In Chapter 9, we'll take a look at natural causes of climate change. For the first part here, we'll look at short-term changes in the single to thousands of years timescales. We can look at sunspot activity, variations in atmospheric dust from volcanoes primarily, human-induced changes in Earth's surface as well. One thing we did mention previously is that the state of El Nino or La Nina does have an influence on global temperatures. More specifically, during an El Nino event, a large swath of warm surface water across the equatorial Pacific causes global temperatures to rise a bit. Because heat always flows from hot to cold, hot ocean is going to give a lot of heat to the atmosphere. And that's something that's not covered here, but we will see that again when we look at the carbon cycle. Introduction. One cannot fully disentangle the natural versus man-made climate shifts in modern times. Humans may be loading the dice, so to speak, make it more likely to get the same role, but natural variability actually gets to have the role. So we need to look at how natural changes led to climate changes in the past and learn something about their potential roles in the future. So variations in solar irradiance. There's three main players on different timescales for that. There's the sunspot number that has a pronounced 11-year cycle with other cycles that are longer. There's the influence of atmospheric dust, which influences how much of the sunlight actually reaches the surface. And then there's orbital variations that are long-term variations of 20,000 years or more that do have effects over long timescales. A 10% change in irradiance could explain all historic climate shifts that we've seen. A 5% reduction could bring a big glaciation, and only a 1 to 2% reduction would bring little ice age conditions. Only a 0.07% reduction in the 80s was the largest recorded change, however. So although these numbers are impressive, these relatively small changes could bring huge changes to the climate, the only change that we've actually seen or witnessed, of course we're always observing solar irradiance, is very small. Here's looking at 400 years of sunspot observations. The more sunspots you have on the surface in the sun, the more solar irradiance. Here's the little ice age we referred to back in the late 1600s, low sunspot number called the Maunder minimum period. And coming out of the Maunder minimum, we go up to some peak, down to another Dalton minimum, and then it kind of fluctuates off and on. It did rise a bit. On average, you can see these giant fluctuations every 11 years with a sunspot cycle. However, on average, it did rise from 1900 to 1950, but more lately, it has been steady and then going down, as shown with this more clear detailed graph here. Here we see the sunspot number decreasing since the 80s, while temperature has actually risen quite a bit. So sunspots actually do correlate pretty well with temperature changes in the last 8,000 years. For example, the medieval warm period, which isn't shown here in 1300, did have high sunspot numbers, and the Little Ice Age, which is shown here, did have low sunspot numbers. So there was a general correlation. Nobody's really established causation, and the real key is that in modern times there is no correlation whatsoever. So here's just looking at that correlation in modern times. Since the 80s, sunspot numbers down on average, temperatures up. Greenhouse gases up, especially CO2. So there's a correlation at least. Just so you can see more modern data, this doesn't have the CO2 data, but it does show that the sunspot numbers are still decreasing. Recently a little bit of a dip up, but overall this large trend downward. Short-term changes looking at variations in atmospheric dust. Now the atmospheric transparency is dominated by how many clouds you have, how much dust you have, and also ozone concentrations, which actively absorb ultraviolet, which is part of the solar beam. Volcanoes are a huge player here. There's a well-known 3 to 5 year cooling period after massive volcanoes with high sulfur content. So a few things you need for a volcano to have a global effect on temperature. It needs to be a massive eruption so that it can get its aerosols past the troposphere up into the stratosphere where there's no weather. If you can get the explosion to do that, then you don't have clouds that are going to rain out those aerosols. Also, it's been shown that having a high sulfur content leads to aerosols that are very effective at reflecting away or scattering away solar light. Clusters of volcanoes caused by active plate tectonics, and this is just the movement of continental and oceanic plates around the globe. The movements of these plates can lead to times of active volcanism, and if you have clusters of volcanoes, they can have an effect, a longer term effect on cooling trends in the past. And I will say, if you look at the medieval warm period in the past, in the 1200s, you do see less volcanism than usual. And then if you look at the Little Ice Age in the 1600s, you do see more volcanism than usual. In more modern times, here's looking at 1958 to 2008, solar radiation transmitted. So in other words, how much radiation gets down to the surface. So this is recorded from Mauna Loa Observatory on the Big Island of Hawaii at about 11,000 feet. At about 11,000 feet, it's well above what's called the trade wind inversion, which means that all the humidity and clouds are generally below this area. And as you climb up to Mauna Loa from sea level, pronounced changes in climate zones as you get up there. It's a very dry atmosphere. Why they chose this place, it's kind of disconnected from the surface, so to speak. You're more representative of the free troposphere at that level of Hawaii. In other words, it's a good place to look at how well-spread volcanic aerosols could actually affect the solar beam at that zone, because you're not likely to have a whole lot of clouds above you at this particular location. Here's the 4 biggest volcanoes within this time frame. Agong here, you can see that solar transmission rates went down with that. And then we see another dip during Fuego here, a smaller dip, not as big of a volcano. These two are very big. El Chucan, you can see the transmission went way down. After that one, huge amount of aerosols in the atmosphere for a number of years there. And this is about a 3 to 5 year time scale here. Pinatubo, also a very large one in the Philippines, brought down the solar transmission rate quite a bit as well. If you're blocking solar radiation from reaching the surface, you're definitely not going to be absorbing as much at the surface, so you could expect cooling globally, and that's exactly what you get with the biggest volcanoes. After the volcano happens, there's a lag, and then it cools for perhaps 3 to 5 years after each large volcano. Large volcanoes that fire vertically can get those aerosols and sulfur dioxide into the stratosphere again, where it combines with water to make sulfuric acid droplets, and they're very reflective. It takes 2 to 5 years for aerosols to diffuse into the troposphere where they can be rained out. So what this means is once in the stratosphere, they can become pretty well mixed, block global radiation from reaching the surface, have a global effect on surface temperature. Eventually they will diffuse, so they'll kind of mix out into the troposphere downward over a long time scale, 3 to 5 years. Once they get into the troposphere with active clouds, active weather, they kind of get scrubbed out and rained out by the clouds. So if you have a large volcano, such as Mount St. Helens, that doesn't fire vertically, what will happen is it doesn't get all those aerosols up into the stratosphere, and the troposphere can scrub them out with clouds, and you don't have a global effect on temperature. Generally speaking, the stratospheric circulation moves from equator to poles. So this makes volcanoes that fire along the equator or anywhere in the tropics more effective at global cooling. So as they go up and hit the stratosphere, the general tendency of the winds in the stratosphere are to push it poleward. So it will mix those aerosols well across the globe if they fire there. If, however, you had a volcano high in the mid-latitudes, which again, Mount St. Helens is a good example, it gets kind of isolated on that hemisphere, and it does not mix very well across the whole planet. So aside from being very large volcanoes, having lots of sulfur, it also helps to be in a tropical zone to have an effect on global cooling. So it is true that volcanoes emit CO2. However, in modern times, we emit about 100 times more CO2 per year. Over longer time scales and without human effects, the CO2 from the volcanoes did have a big effect at times when it was unbalanced by weathering processes, which we'll take a look at in the carbon cycle, but these are long-term processes that don't really have an effect in modern times and the timescales we're dealing with today. So you can clearly see here, while we saw huge reductions in solar transmissivity and significant drops in temperature, you can see during the largest volcanoes, there's hardly any change in really the path of CO2 over time. This overarching trend here upwards is fossil fuel usage, and the volcanic explosions, even those are the biggest ones we've seen in this time, really didn't influence that trend. Last question, in what ways are humans changing Earth's surface energy budget by land changes? There's been clearing of forests by hunters and gatherers and then farmers later in the times, urbanization, desertification, artificial lakes, irrigation, which artificially puts a swath of water on a land surface which might otherwise protect that water, mining, etc. There's big effect on albedo and what's called the Boeing ratio. So the Boeing ratio just considers for a land surface, if you add some solar radiation to it or add some heat in any way to the surface, how much of that will actually go into heating the overlying atmosphere, sensible heating going from the surface to the atmosphere, versus how much of that heat will be used to evaporate, say, water. So in that sense, you can think of a hot, dry parking lot. A lot of the solar radiation will go into sensible heating of that surface, which will ultimately go into sensible heating of the atmosphere above it, so that has a high Boeing ratio. Alternatively, if you had a really moist surface, a lot of the solar radiation coming into it is actually just going to be used to evaporate water, and it's not going to raise the temperature of that surface, so it would have a low Boeing ratio. By changing land surfaces, scrubbing away vegetation, taking down forests, you're definitely changing the balance of sensible versus latent heating that you might see in those land surfaces. And you're also changing the albedo. What's been found over time is that 1 degree Celsius of cooling has happened due mostly to a rise in albedo. And so we can look at this graph and see what kind of changes have happened. Going from savanna to desert, this would be kind of grasslands with interspersed pockets of trees, getting changed to desert in what's called desertification. 2% of Earth's surface has done that, and the change in albedo, it's raised the albedo. Deserts are more reflective than savannas. Going from temperate forest to grassland, that might be something a farmer does or somebody who's raising cattle. 1.6% of the land surface, again, the albedo goes up. Tropical forest to field or savanna, this happens a lot in the Amazon, where they take down rainforests and replace it with savanna in order to raise cattle, because Brazilian beef is well sought after. That's 1.4%, and that changes the albedo in a positive way as well. Forest is really low albedo, savanna is a bit higher. Here's a graph looking at some of these conversions from 1700 to 2005, land cover gains. The reds here show conversion from forest to croplands. People have been modifying the land surface in Europe and the United States, southern Canada, all over the world, to make it conducive to grow crops, and that's what's shown here. The blue here shows the albedo change as a result of all this, and they do show the blues are positive albedo changes, and so you're seeing increases in albedo, especially in Europe, United States, and parts of southern Canada. Here's a desertification vulnerability map. Essentially what this is showing is fringe lands along the world's desert, where the vegetation is just barely hanging on. It just barely has enough precipitation to persist there, and so that's vulnerable. If it gets any drier than it already is there, the plants will die out, and this will tend to be covered by more extreme deserts. So the southwest part of the United States is definitely a place that's vulnerable. The projections are that the southwest might see mega droughts in the future. So looking at this animation from Bloomberg, we'll see the effect of greenhouse gases on the atmosphere. All right, here's the observed temperature trend first shown, the measured or observed land and ocean temperature. This is looking at orbital changes. We're going to have a look at this in the next lecture. Next is this expected temperature changes from solar activity. You can see not a pronounced effect there. Volcanic activity, that's what we were just talking about. You can see these periodic plunges or cooling events. However, they certainly do not explain the long-term trend that we've observed in temperature. If you combine those 3 natural variability modes, you get something that actually does not raise the trend at all. In fact, it might even cool it a little bit. You can look at deforestation, which isn't natural, but it is a process that's not greenhouse loading. The rise of albedo has cooled us just a little bit due to land surface change over time. So ozone, natural ozone high in the atmosphere, blocks harmful sunlight and cools things a little bit. However, closer to the Earth, ozone is a greenhouse gas and traps in heat. The overall effects of man-made ozone pollution has been to warm just a little bit because it's a greenhouse gas. Aerosol pollution, like I mentioned, aerosols do have an effect on climate. So it is a cooling effect. That is our best guess. So again, these are the combined effects of just simply loading the atmosphere with dust, which is blocking sunlight, but also having that dust attract water and have more prolific clouds as a result of aerosol loading. Here's looking at greenhouse gases and our expected temperature as a result of loading more greenhouse gases. This does not consider any of those other natural variability, just expected temperature rise from increased greenhouse gases, and that overshoots the observed trend. Now we can combine that with some of the natural variability modes, and you can see a much better match with the observed trend. And now we can put everything together: orbital changes, solar changes, volcanic changes, land use, or aerosols, ozone, and the greenhouse gases. And you see a pretty good fit to what's been observed over time. Key points from part 1 of chapter 9, looking at natural variability in climate. Short-term changes, sunspots linked to temperature changes roughly over the last 8,000 years. They certainly do not appear to be influential in modern warming in the last 100 years. Volcanoes do cause short-term cooling, at least the largest volcanoes, and clusters of them, when you have extreme volcanic activity, can cause sustained cooling. Human-induced changes in the Earth's surface have raised albedo and cooled us about 1 degree Celsius over the last 200 or 300 years. Modern warming appears completely unrelated to natural variability. It really appears that greenhouse gases are leading the charge towards increasing temperatures, and this is being moderated a little bit by other natural variability modes and some other land surface changes.